these three things. Why this field is important and what has been done and what's next. So I can help you to, yeah, maybe, okay, succeed in this field too. Let me start from autonomous driving, end-to-end autonomous driving. Autonomous cars are very important, yeah, because they are the first large-scale embodied AI applications that has changed our life and is going to change our lives. And but it has not yet. So what's been missing? The community has been discussing about end-to-end architectures for autonomous driving, both in academia and industry. Why? Because it's a potential to scale to endless data. So that's gonna solve the problem in the industry to allow us to allow autonomous cars to the airport level to drive anywhere on the earth. So end-to-end autonomous driving is an important topic. Yeah, and this trend has already been validated in the history, academic history. Yeah, it's just like faster RCN vs RCN and the CN vs backwards. Okay, this is a very good paper from Open Drive Lab, a TBAMI paper. Yeah, it gives a good overview of end-to-end autonomous driving. Yeah, but
我这边 mute 一下，有回音。
那边 on mute。
你那边 unmute， 我这边 mute。
没有。
啊，这个是吧 ？Okay, good. Okay, but end-to-end autonomous driving has a very big issue called interpretability issues. Yeah, here is a paper, the copycat problem from Professor Gao Yang's group. Okay, yeah, since every company, nearly every autonomous driving company is trying to develop their autonomous driving systems in their cars. Engineers, scientists are struggle with within their daily R&D lives because yeah, nothing works and no one knows why. That's what's happening with end-to-end systems. Yeah, there is a famous problem called copycat problems. If we train an autonomous end-to-end autonomous driving system in the intersection crossing, yeah, and it stops just because the other vehicle stops around them. That's called the copycat problem. And the end-to-end system fails to learn that it stops because the traffic light is red. Yeah, because the traffic light is so small in the camera stream. Yeah, and this is just one corner case the R&D team is encountering in their daily life. And how about other corner cases? There are so many corner cases in the R&D procedure of end-to-end autonomous driving systems, and nothing works, and no one knows why. So here comes the holistic video understanding for autonomous driving. Yeah, according to my experience, communication with the industry, the most valuable part about this kind of vision language systems for end-to-end autonomous driving is to interpret why the system fails. That's quite different from the multimedia community. Yeah, since I saw many many good researchers in the vision language video language research area, and they all aim for stunning multimedia applications. But this is somewhat counterintuitive, maybe for some of you. Video language systems, the biggest application is to help, engineers interpret what's happening, inside the system. Here comes one of my paper published in last year's ICRA called ADAPT, Action-Aware Driving Catching Transformer. Yeah. Here is a demo video of this whole system. Okay, this is an end-to-end autonomous driving system. Yeah, it predicts the acceleration and other control signals, and it says while it drives along the road, the car pulls over to the left and stops because it is parking. Yeah, the red part in this task is called a description, and the blue part is called narration. It's called justification. Sorry, the first, yeah. Okay, so it's deployed in autonomous end-to-end autonomous driving systems. The car starts to move and merges right because there is a car in its lane. Yeah, and when it enters the intersection, yeah, it shows some good zero-shot capabilities. Yeah, bikers are very rare in the training set, but it successfully predicts this. Okay, here is the architecture. Yeah, this architecture takes the camera streams into a video swing transformer, and there are two string outputs. The first part is end-to-end autonomous driving. It predicts the counter signals, speed, course, and acceleration. And the second part is a vision language part. It predicts two sentences. The first one is a narration, and the second one is reasoning. So that, okay, the previously mentioned dynamic is somewhat addressed. Okay, using this kind of systems, engineers can diagnose what's happening when nothing works and no one knows why. Okay, and technically speaking, since the reasoning part is dependent on the narration part, we use a coarser attention mask as shown in the left to right corner. And for video attention, we use for video tokens processing, we use sparse attention so that it be trackable. Okay, here are some ablation studies. Yeah, the left top one shows that action awareness matters for video caption, for driving video caption. Yeah, that's quite understandable if you can. Yeah, if you notice the car is decelerating, of course you can predict the control signal. Yeah, in its natural language output. And yeah, the left bottom part shows attention mechanisms impact. And on the right side, we also show some challenging cases. Yeah, it's in the data set for nighttime and for rainy days. Yeah. Okay. And since this is a tutorial, and I'm gonna show you what's happening behind this paper. There are several follow-up papers, and this one is called Drive GPT-4. Okay, it's outperforms adapted by a large margin. Of course, the contribution is that it uses a large-scale pre-training step. And the right side is another paper called RAG driver. Yeah, RAG is very popular in today's natural language processing. Okay, there is a database, so we can retrieve some seminal things and input them to the transformer. Okay, yeah, notably, this RAG scheme can outperform adapt in a zero-shot manner, yeah, by a very large margin. Okay, so these are some follow-up methods from the community. And this one, okay, is a recent paper from my own group called Hint 80, published at Cora 2024. Okay, holistically aligned interpretability for end-to-end autonomous driving. Okay, it's a one network for all video language understanding tasks that have been defined by the academia. Okay, so this is a driving assistant that speaks to the customer or the engineer. You can ask your autonomous driving cars any questions. What's happening? What about the perception, the planning, the decision-making part? Okay. Okay, so here are some more details about this scientific publication. The first, yeah, is about the scheme comparison. Alignment, everyone knows alignment is important for research field for multimodal foundation models. And yeah, to the best of knowledge, Hint-AD is the first one that systematically addresses video language alignment tasks in one network, and including all tasks we have been defined, like yeah, captioning, dance captioning, driving explanation, and command prediction, and we have aligned them with all intermediate representations have been defined in the autonomous driving community, like bounding boxes, tracklets, occupancy, trajectory predictions, and the map elements. Okay, they are holistically aligned, so that's the name. Okay, here is the architecture. The architecture, first on the left side, it's a typical end-to-end autonomous driving system. It predicts some intermediate outputs for perception planning and yeah, prediction. And we fuse all of these tokens in a token mixer. And finally, we align these autonomous driving representations, which are natural language representations using a llama adapter, actually. Okay, here is a prompt. We can ask the system any questions you care about it, and it will give you the result you want. Here are all the tasks we address, including driving explanation, 3D dance captioning, detect every box and describe it, and real question answering. You can ask your autonomous car what's happening here, and the command prediction. Okay, and we have achieved new SOTA results. Yeah, just like recent paper style. Yeah, we reach new SOTA results because we train all of this data. Yeah, then they help each other. Okay, so this is the first part for holistic video understanding for autonomous driving. And yeah, the maybe okay, maybe a counterintuitive thing is this kind of things is most useful for debugging. Okay. So the next part, video simulation for autonomous driving. And yeah, the first part, yeah, the first half is about diffusion based, also known as driving world models. Okay, video diffusion models is most popular, hottest topic in 2024, arguably. And here are some results from the community. Yeah, these are generated. This paper is called Vista. Yeah, it's done by the Open Drive Labs team. Okay, it can generate very photorealistic video diffusion results, just like Sora and Kling. And we are asking the question, what's the next big thing? Yeah, so just like the generic video diffusion community, the next big thing is controllability and the physical awareness. Yeah, just like what Professor Chuang has mentioned, physical awareness is very important for video generation, and the controllability. Yeah, everyone wants controllability for multimedia applications. Maybe I can control this. People work this way, work that way, or change his hat or something like that. Okay, so here comes my latest research on this SCA world model. Structure-aware, collaboratively aligned driving world model. Okay, here are some take-home messages of as a new state-of-the-art driving world models. Okay, we identify very simple and effective trick to improve the video consistency and the structure awareness. Yeah, using self-supervised depth estimation. Yeah, it's a wide community, and we show that at least for the specific autonomous driving scenarios, using this kind of regularization can improve FVD by relatively by about 10%. And our method also builds upon the state-of-the-art quality and allows all kinds of controllability you can imagine, including post, box, max, and the language condition. So here is the architecture. And yeah, on the above side, we can see that we encode the text condition, post condition, layout condition, box condition, all kind of these things, into interpretable encodings, and cross-attend them with noise, so that the DRT architecture, the video DRT architecture can generate the video we want. And on the bottom side, we use a self-supervised depth estimator to improve the structure awareness. Okay, here's another interesting paper. In this page, we show text condition, post condition, layout condition, and edge condition. Yeah, here are some final conditions we're pursuing semantic masks. Semantic masks can be generated by conventional rendering pipelines. Yeah, and so we aim to use this kind of input to generate very photorealistic and totally controllable driving scenes. Yeah, it's finest control, and you can guess which one is generated and which one is real. And I guess it's very difficult to tell, okay, because we have improved this task to a very high FID level. So this is the results, okay. So this is a paper published in this year's ECCV. So this is state of the art. For example, for cityscapes published best results is 44 FID, and we can reach new state of the art of 10.5 FID. Yeah, so the photorealism is improved to a new level. And why we can do this is that the secret source is that we employ the spatial category called joint prior. Yeah. I guess you must know that diffusion models predict noise residuals from a noise initialization. And typically we use a white noise, Gaussian noise initialization. Yeah, but for autonomous driving, since there is a very, very strong prior, because just like on the above side is always sky, and on the lower side is always road, and on the left right side it's always buildings. So okay, we calculate the prior, just like this figure. Okay, if this in this case there are some typical categories to be placed here. So we calculate a specific mean and variance for noise initialization at that place. Yeah, so we can push the semantic image synthesis quality to a very, very high, number. Yeah. Okay, so this is the second part about the diffusion-based video driving video generation. And finally, for the third part, is nerve-based. Yeah, nerve-based or Gaussian splitting-based. It has better controllability. Okay. Okay, so here is the motivation, and there are many corner cases to be addressed in real-world autonomous driving systems. And what's worse, it's very difficult to connect this kind of data, like the left one. Okay, it's very expensive to place this kind of things on the road and take a photo. And existing simulators like Kala, it lacks photorealism. So here comes neural rendering. Okay, our our algorithm Mars, okay, is published last year, and it's the first modular autonomous driving, nerve-based autonomous driving simulator. Okay, it also won the best paper runner-up award on CKI 2027, 2023. Okay, it has three important features. It's instance wire. Yeah, in this field there are some papers that are not instance wire. Okay, so it only models dynamic road, static road things. So it's less used. It's not that useful for autonomous driving simulation, but still useful for some specific cases like camera view shifting. Okay, and the most important feature of our code base is that it's modular. Okay, it's just like Nerve Studio. You can select your backbone, your nerve backbone, and your sampler, and everything else, your supervision signal, so that yeah, you can easily test your ideas in a modular manner. Okay, here is a video of our Mars simulator. Okay, it can reconstruct the scene in a very photorealistic manner, and most importantly, it's instance aware. Yeah, every car, every vehicle, everything in this world, in this thing is a separate nerve, so you can place them, rotate them. Okay, and without a sensor sim-to-real gap. Okay. There are also many follow-ups in this field, and this field, like this one from Professor Peng's team, okay, street Gaussian, it switches the backbone from nerve to 3D GS, to the 3D Gaussian splatting, and it uses a similar formulation to train a separate Gaussian splatting model for each car, so you can edit it. And as shown on the right bottom side, the Gaussian splatting is very fast. Yeah, and if you properly train, it also gives better PSNR values, and as shown on the left bottom side. Here's another paper published in this year's CVPR. It also outperforms Mars. Yeah. And on several other data sets, the secret is that they use zip nerve backbone. Yeah, the zip nerve backbone is very powerful. It's very powerful. It can anti-alias the detail artifacts. Okay, in both far side and the near side. And this is a paper called Hearts. Yeah, published at this year's CVPR. Yeah. By Professor Liao Yi's team, and the secret source is to use more supervision signals. Yeah, and as you can remember, we can render depth, render semantics, but in this thing they use optical flow and many other supervision signals to further improve the rendering quality over Mars. Okay, and this is a recent paper also from I don't quite remember. So here is the state of this field, neural rendering for autonomous driving and the simulation. The ultimate goal is to generate important corner case data, so we can train our autonomous driving systems better. Okay, we can switch the backbone to 3D GS, use more training signals or zip nerve or things like that. So that's the state of the this field. But what's next? Okay, here let me introduce you the CVPR highlight paper of our group. Okay, called Chessim. Yeah, Chessim can edit autonomous driving things using natural language. Okay. Yeah, just like this, the user command is to remove all the cars in the scene and add a posture driving the wrong way towards me. And additionally, and also it can, address this kind of highly abstract, high-level command like create a traffic jam, or in a nerve-based 3D world. Yeah, it also can. It also support multi-round communication, just like this. Yeah, maybe in the second round, the user changed his mind or her mind. Yeah, in the third round, the user wants to add another vehicle to the left. Things like that, just like how you use ChatGPT. Yeah, And here are some rendering results for foreground. Yeah. And this is some background rendering result. How we do this? Maybe it's simpler than you might think. Okay, so this architecture use many ChatGPT agents to write code. Yeah, teach ChatGPT to write code. Code is much simpler than you think. Okay, so build a ChatGPT agent. You only need to prompt it. So you are agent that finishes this task, and your task is to do this, and it turns into this kind of agent. So our system has a project manager agent. It will split high-level commands into six different detailed commands, and these commands will be sent to the other six ChatGPT agents. Yeah, each of them has a code template. Yeah, it writes codes, and it has a code templates. Most of the code has been written there, and the only job of this agent is to feed the scene specific parameters into the code split, so that this system can edit autonomous driving scenes according to high-level commands. Yeah, so yeah, basically this is what's happening in autonomous driving simulation, this field. Yeah. Okay, here is another somewhat interesting paper from my group. It's a Gaussian splitting field that can transfer from the drone view to the road view. Okay, we can see it again. Okay, and specifically to this paper, it's drone assisted road Gaussian splitting with cross view uncertainty. Yeah, for autonomous driving simulation, our ideas is to use drone images to improve it, but unfortunately, just adding more drone view images into the whole system can degenerate the performance. So yeah, we've introduced a cross view uncertainty. We calculate the ensemble-based uncertainty, the road view, and backpropagate that to the drone view so that we can focus regions that would be helpful for the road scenes. Okay, in the last page, I will show some more embodied AI results. Although this paper, this talk is mostly about autonomous driving. It's a very interesting paper from my group, published at IROS. It's pre-afford. So this is a pre-grasping. Grasp something that is not graspable on a table. Okay, so our algorithm can learn to exploit the geometric environmental features like a table edge, like a wall, like other geometric features. Okay, so this is the architecture of our algorithm. It has two affordance networks. The first one is a pre-grasping module, and the second one is a grasping module. It both predict affordances. Yeah. Okay, so here is the end of my talk. Okay, let me briefly review what have I covered: video simulation and holistic understanding for autonomous driving, and a little bit embodied AI. Okay, yeah, and feel free to connect with me. Yeah, and 3 topics. Yeah, just a recap: holistic video understanding and diffusion and nerve-based video simulation. Thank you, everyone.
Many thanks for the great talk. Okay, any questions? Okay, maybe I first go through questions, very quick questions. What do you think utilize the framework to unify this kind of understanding and also simulation task for autonomous driving?
Yes, that's a good question. And I guess many people are talking about this because in these years, natural language processing has unified understanding and generation. Yeah, and that's still quite difficult for computer vision tasks because output space is structured. Yeah. For now, I do not think we should blindly follow the NLP community to build this kind of a unified framework. Instead, we should pursue omni-supervised learning. Yeah, omni-supervised learning leverage enormous unlabeled data and it implicitly builds a generative model so that understanding performance can be improved.
Okay, I have another questions for the diffusion-based module. Because I'm also doing some research on the diffusion-based module, and one drawback for this kind of model is the efficiency. The inference time maybe is very slow. So when you adapt to the autonomous driving, you may need some real time or some efficient output. So how to deal with this kind of situation with diffusion-based model?
Yeah, actually for autonomous driving, most of this existing research focus on the cloud side. Yeah, cloud side. If during R&D, we use this kind of diffusion methods to generate data to improve models. And of course, we are also pursuing online simulation. Yeah, online simulation is a very cool topic in robotics community. Yeah, maybe a robot or autonomous car run into a situation. It can simulate the world in his own brains. Yeah, so that but I think we have not yet reached that point in the next 6 months. And of course, that's a good question. We can, we sooner or later we will address this efficiency problem. Yeah.
Okay, thank you. Any other questions from our audience?
So, Professor Zhao, and I'm Hao Zhao. Yeah, and since you can generate some corner cases with nerve models or induction models, do you have any idea to utilize this corner case?
Yeah, that's a good question. Yeah, for autonomous driving, the sensor simulation improvement is also is typically deemed marginal. Yeah, using corner cases can only improve the performance by 2 or 3 MAP. So that's a typical criticism. But recently the field is switching to closed loop autonomous driving simulation, and in that setting, I think things would be that would be a game changer. Yeah, if we use a closed loop end-to-end autonomous driving simulator, it would directly improve the drive score, yeah, success rate, things like that. And bypassing the criticism that generated data can only improve detection MAP by only 2 points, this kind of thing. Yeah.
And also, I'm wondering whether some techniques like norm detection can improve the model to deal with these corner cases.
Yeah, I think anomaly detection is highly related to autonomous driving simulation. But for now, according to my experience, okay, the most critical part is dynamics. Yeah, the agent dynamics. That's the most critical part for autonomous driving simulation instead of rendering quality. So and that's still understudied. Yeah, and detecting anomalies in a large scale agent dynamics data set, like my Inter2 data set, I always want to do this. Yeah, it would be a great future direction for the anomaly detection community. Yeah, that's my opinion. Yeah.
Okay, thank you for the questions. Please. You can use that microphone.
Okay, thank you for a wonderful talk, Professor. And I have a quick question. For the diffusion-based generation, I saw current pipelines are just generating videos from some 3D signals such as the roadmap and the bounding box. How about the multimodal generation? For example, we not only generate videos, but also the LiDAR or occupancy signal from some simple BV layout or some text promote. What's your opinion for such generation? Because I thought it's more practical generation pipelines because most of the downstream tasks, they need multimodal information for the training and data augmentation. Yes.
Yeah, I think that's a good future direction. Actually, there is a neurons paper I get from William Freeman's group called 3D aware diffusion, things like that. Okay. Yeah, I think the future paradigm would to use diffusion models to generate occupancy signals like that, and we render this into RGB signals. Yeah, so that we can get a better controllability, 3D controllability. But for now, it has not been done yet. Maybe several technical challenges like resolution, data, things like that. But that would definitely be the good future research trend.
Yes, the occupancy-based generation, I have work on my hand. I'm just targeting on it, and I think that's true. There is some problems, and maybe later we can communicate more on this.
Yeah.
Thank you.
Okay.
Okay. Any other questions? Okay. So if there's no more questions, let's thanks Professor Hao Zhao again. Okay, so here's our speaker this afternoon and start at 2 p.m. So,
okay, sorry, I just entered the Zoom meeting. So